Okay, so welcome back. We're going to actually do some examples of implicit differentiation. This is going to lead into something called related rates. And so within related rates, we often have to differentiate. Almost always it's with respect to time. But again, we're going to be differentiating with respect to something that isn't one of the variables, or it's not all of the variables. So an example of how we could do this, imagine that, my good friend Jad found himself in a rectangular prism of a room. Okay, so we've got this, it's kind of like the trash compactor that we had on Star Wars. So here's my good friend Jad inside this room. And the way this room works is that its walls are contracting. So this wall here, this wheel here, is going to be moving in. Now it turns in that this wall is moving in at 1.5 meters per second. And the back wall, it's contracting in, it's going to be coming in at maybe 1 meter per second. And then the roof is not going to be changing at all. It's going to just be static. So when Jad enters into this room, it has the following dimensions. It's 2 meters tall. It is going to be, let's make it 6 meters wide, and it's going to be, 4 meters deep. And what we want to know is we want to know at what rate is the volume of this room going to be changing. So I want to know what dV with respect to time is, dV by dt. Okay, and again, this is a related rate problem, but we're going to see, how this works out. So what we're going to have to do is we're going to have to find an expression that represents what what we're looking for. So in this case, we know that volume is equal to, this is just a basic rectangular prism, so length times width times height. So we've got volume equals length times width times height. And we know a bit of information about this. We actually know that if I call this dimension here, so I call that length, and I'm going to call this dimension here, I'm going to call that width, and then clearly this dimension over here is going to be height. I know that the dl by dt, the length, it's actually changing. It's getting smaller at a rate of 1.5 meters per second. So I'm going to put in 1.5 meters per second. We'll have to be really careful. It's getting smaller at a rate of 1.5 meters per second. So it needs to be negative 1.5 meters per second. And then we know that what we have here is that the width, this dimension here, the width is getting smaller. So dw by dt it's decreasing at it's decreasing at 1 meter per second. So 1 meter per second. Now we're going to have to be really careful with our language that we use in this particular unit, because it's decreasing at 1 meter per second. It's not decreasing at negative 1 meter per second. So again, this is a lead in very much to what related rates is. And we're going to find out that with related rates, we're always going to phrase our answer so that we can state it positively. So if we find that it's decreasing, we're not going to say that the volume is decreasing at negative 5 meters cubed per second, because if it's decreasing at a negative, that means it's actually increasing. So we're going to be really careful, but I'm going to model that a bunch when we're working through. Now, what's interesting here is dH by dt, well, it's static. It's actually not going to be changing. So dH by dt, it is actually going to be 0 meters per second. So it's not actually changing. We're going to shortly look at an algorithm for solving related rate problems. And when we get into that, we're going to find out that anything that's considered static, we can treat as a constant, and we can substitute in that value before we differentiate. So I'm going to go ahead and I'm going to do that now. So volume is equal to 2LW, where the 2 is actually what the height is. So I want to differentiate this with respect to time. And so I'm going to have to give some information. I'm going to say, okay, how about when the room is, how about let's change that to, has a length of 3. 3 meters, at what rate is the volume changing? Okay, so when the room has a length of 3, at what rate is the volume changing? Well, we can actually infer from that that that's got to be 2 seconds in, because it was 6 to begin with and it's gone in for 2. So we can then kind of say, what do we know? Well, we know obviously that the length is 3. I mean, it's given up here. But we also know in this case that the width is going to have to be 2, because we've elapsed 2 seconds and the width is decreasing at 1 meter per second for 2 seconds. So it's going to take us down to a width of 2, so meters and meters. So I'm going to come back here and I'm going to differentiate this with respect to time. So the derivative of v, if it was just a regular, it's going to be 1. So I'm going to be really explicit. I'm going to say 1, but I'm differentiating a v with respect to time. So that's going to be 1 dv by dt. Now, this is going to end up having to be a product rule question, because we had 3 variables, but because this one is static, I got to just kind of substitute it right off the bat. I can't, again, I'm going to lay this out again later, but I'll say it now. If you think about a variable, whether we get to substitute it before we differentiate or after we differentiate it, it comes down to whether that variable will have the same value if the problem were allowed to continue for any more time. So in this case, if we think if it was allowed to go for another second, is the height going to still be the same height? Well, yeah, it is, because the height's not changing, it's 2. Whereas the length and the width, well, those values would differ, of course, because as time progresses, the length and the width change. So I can't substitute in for them. So anyways, back to where we were. So we're going to differentiate. So there's going to be product rules. The derivative of the first is going to be 2, but we differentiated in L, so dL by dt times the second, so first times the second. I didn't give myself very much room here. Plus the first, which is 2L, times the derivative of the second. Well, the derivative of W is just 1, so 1 times dW by dt. So there's my actual derivative, right? So I've got this derivative now, and so I'm just going to rewrite it a little bit cleaner. So 1 times dV by dt is obviously just going to be dV by dt. And that's going to equal, I'm going to say 2 dl by dt times w plus 2l dw by dt. And I wanted to know when the length was 3 meters. And so we know that the length is 3 meters, but at that time simultaneously, we have that the width is 2 meters. So I'm going to go back here and I can actually substitute these values in. And so we know that dl by dt, we know what it is. It's actually negative 1.5. So I can substitute in negative 1.5 times w. Well, in this particular scenario, the w is 2. Plus 2l. Well, we know what l is. We know that l has to be 3. So there's 3. And dw by dt is negative. And negative 1. And so we're going to substitute in negative 1. So then we can just simplify. So 2 times negative 1.5 is negative 3, times 2 is negative 6. So we're going to have negative 6. And then 2 times 3 is 6, times negative 1 is negative 6 as well. So negative 6 times minus 6, which is negative 12. So we know what the units are here as well, right? This is volume, and we were given in meters. So this is going to be negative 12 meters cubed per second. So the resultant value is negative, which means, of course, that the volume itself is decreasing. Unsurprisingly, we have seen that the room is contracting. So when we're going to deal with related rates problems, which this is just an example of related rates, we need to actually have formulaically we need to create a concluding sentence. So we would say the volume of the room is decreasing at 12 cubic meters per second. Now, be really, really careful. I'm not going to say that it's decreasing at negative 12. The positive or negative is going to be taken care of because we're going to choose our words very, very carefully. Because it was negative, we said decreasing. So please don't say the volume of the room is decreasing at negative 12 meters per second, because of course that would be an error. Okay, so we don't want to actually do that. So there is another example. So let's do one more example of this, and then I'm going to assign some practice questions for you to work on. So another example, imagine that two people were out riding their bikes and they've decided to take off, and they're going to take off at the same position to begin with. One of them is going to go never eat shredded wheat, so never do east at, I don't know, how fast does a bike go? 5 meters per second. And then we've got over here, well, we've got Erica on her tricycle. And so Erica is going to be going due south, and she's booking it on her tricycle, just pumping like mad, and she's going at 2 meters per second. I would like to know, let's say, here would be an example of a question. How quickly is the distance between the cyclists changing after they have ridden for, let's just say, make it easy, 10 seconds. Now, because we had that this was due east and this was due south, we know that we're going to be forming a right triangle. Let's see if I can do this. Oh, sweet deal, look at that line. So what we're actually really looking for is this distance here, how it changes. So I want to find, in this scenario, I want to know what is dx by dt going to be equal to. Okay, and I can call, it doesn't really matter, I'm going to call this A maybe, and I'll call this B. And so we actually know, so this is our find, this is our know. We know that dA by dt, well, we know that it's given, it's 5. Now in this case, it's going to be positive because A is getting bigger. So again, the sign really makes a big difference. And then similarly, we've got that dB by dt, it is 2, and again, it gets to be positive because it's increasing. So I want to find out what that is. Well, we're going to have to find something that relates these things. Well, clearly we know Pythagorean theorem. So I know Pythagorean theorem is c squared equals a squared plus b squared. But in this case, we can actually substitute in. Now, here's the thing. None of these things are static. So there's nothing that I can substitute in right off the bat. None of them are static. So I'm going to put in the actual variables here. We're going to say, so in this case, we set it up. It's going to be x squared is equal to, luckily I called them a squared and b squared. Now, historically, what we did is when we did problems like this before, we would actually have to take the square root of this and isolate for the quantity that we're looking for. But what's kind of cool here is that I don't actually need to do that because I can differentiate with respect to time right away. So if I differentiate with respect to time, well, the 2 is going to come down, so we're going to get 2x, but x isn't time, so it's going to have to be dx by dt is equal to 2a times dA by dt plus 2b dB by dt. And we're going to substitute things in that we know. Well, look what we know. We know, for instance, dx by dt is what I'm after, but I do know what A is because we know that the top cyclist was moving at 5 meters per second and they get to go for 10 seconds. So that means that A at this particular snapshot is going to be 10 times 5, which is 50. And we also know what dA by dt is. It's 5. So I'm going to put in times 5. Plus 2b, well, b, again, it ran for 10 seconds at 2 meters per second. So b is going to be 20. And times dB by dt, well, dB by dt is the rate of change of b with respect to time, so that's going to be 2. Now, I should have chosen 4 and 3 for the speeds to make this easier, but x, we can actually figure out what x is going to be. So x is going to be the hypotenuse of the triangle at that particular time. And so we know that, wow, it's a lovely right angle. So we said that this side is 50, this side is 20, and this is going to be x. So we know that x is equal to the root of 50 squared plus 20 squared equals. Now I've got my handy dandy calculator here. So we're going to have that x is equal to the root. So the root of 50 squared plus 20 squared. So we're going to take the root of that. So 53.85. So the hypotenuse on this particular triangle is, oh my God, I have the attention span of a gnat. What is it? 53.85. 53, oh, that's not a nice 3. You know what it is. 385. So I can go back here and I can say, all right, well, that's what my x value is. It is 53.85 times dx by dt. So then to solve, we're just going to drop all that in. So we're going to get over here, I guess, that 2 times 50 is 100 times 5 is 500. Plus that's 40, 80, I guess. So let's just make this 580, save me a step. And then I'm going to divide both sides by whatever that is. So divide by that. So I don't know what it would be. I guess it would be 107.7, I think. Let's pretend that it's at 107.7 dx by dt. And that is the rate of change. So I'm going to grab my calculator. I'm actually going to check that. So 2 times, so just do that, times 2. 107.7, yay team, I won. Okay, so I'm going to do 580 divided by 107.7. And we're going to find out that it's 5.34. So the rate of change of the distance between those cyclists is 5.39 meters per second. So 5.39 meters per second. So there's an example of applying related rates, or excuse me, implicit differentiation in a related rate problem. So I'm going to sign off the video there, and you're going to find on Google Classroom the homework questions I would like you to use. Thanks.